The new pictures caught by the James Webb Space Telescope have shocked scientists. Instead of expanding our comprehension of the universe, these pictures uncovered an upsetting reality. Our current understanding is inadequate to make sense of the idea of the universe in its beginning phases, where the theory of the universe's origin reaches its limits. This compels us to think about new speculations about its starting point. The inquiry emerges as to how the universe was formed exhaustively and why this new revelation challenges even the most experienced space experts to figure out more about the Big Bang and the progressive subtleties of the discovery. We should review the idea of the Big Bang itself. Contrary to popular belief, the Big Bang was not a blast in prior space. Rather, it was space itself that began around 13.8 billion years ago, alongside matter and time, from a unique peculiarity in physical science and cosmology, a peculiarity that describes spots where gravity is so extraordinary that the curve of spacetime becomes infinite. Today, after billions of years since the start of the universe, we observe that our cosmic home is part of a major interaction. For specialists, this represents a fundamental component of the universe, since its very presence and its seemingly unending expansion are significant to comprehend. The universe isn't venturing into prior space, rather, space itself is continually expanding in size. According to traditional theories, the first stars began to shine somewhere between 200 and 300 million years after the Big Bang, marking the end of the so-called Dark Age. This was when the first luminous celestial objects clustered together to form mature galaxies. However, how rapidly these galaxies developed remains an inexplicable riddle. A significant piece of information emerged through the first pictures captured by the James Webb Space Telescope in July 2022. Specialists reported that the telescope had identified various galaxies, some of which had already existed around 300 million years after the formation of the universe. However, compared to the cosmic structures that formed billions of years later, these early galaxies were significantly smaller and less massive. This fits perfectly with the scientific model accepted by specialists. The density of matter in the youthful universe was just not sufficient to lead to galaxies the size of those observed today. What started as the discovery of 6 dazzling redshifted luminous spots from James Webb ended up triggering one of the most significant cosmic emergencies of recent times. Although these newfound galaxies are similar in age to previously recorded galaxies, they are nearly as gigantic as our own Milky Way galaxy. This has created a captivating mystery in galactic astronomy. After examining a series of pictures captured by the near-infrared camera, specialists identified the previously mentioned light sources. Using redshift, researchers determined that the light from these objects took more than 1 billion years to reach our eyes on Earth. Therefore, we are dealing with structures that had already existed between 570 and 700 million years after the confirmed Big Bang. By examining the characteristics of these structures, it was concluded that the Webb telescope had captured 6 very early galaxies in the picture. Shockingly, these galaxies were so enormous that they defied traditional assumptions of cosmology. Rather than finding the expected dwarf galaxies, structures were identified that were nearly as massive as our own Milky Way galaxy, despite having formed early in the epoch. If we continue to analyze the data gathered by the James Webb Telescope, this gravitationally bound collection of stars was already more than 10 billion times the mass of the Sun at that time, with one population surpassing the 10 billion solar mass mark. However, whether this possibility is considered, the mystery is not fully resolved. Even in this scenario, there would be significantly more cosmic mass in the early universe than previously expected, presenting a puzzle. The identified objects contradict nearly all conventional cosmological theories. Even if only one of these galaxies turns out to be authentic, it would challenge our previous assumptions to explain the presence of these structures. Moreover, the density of matter in the early universe would have to be multiple times greater than previously accepted to explain this phenomenon. Another similarly strange explanation relies on the idea that these galaxies formed in a way that is still completely obscure to us. These discoveries and the debates surrounding the Big Bang are driving more analysts to distance themselves from this theory. Many space experts with alternative views are puzzled, and their perspectives are often heard in scientific journals. Even those who express doubts about existing theories are frequently labeled as unwarranted oddities. However, it is evident that even specialists who still defend the Big Bang theory are continually confronted with questions without clear answers. These questions include specific issues such as why and how, 13.8 billion years ago, something literally emerged from nothing. Could something truly start from nothing, or was there some triggering event, or was it all just an accident? Stephen Hawking pointed out that the concept of time as we know it began with the Big Bang, hence this process could not have been triggered by something else or by an external cause. A similarly ambiguous question relates to the uniformity of radiation and density throughout the universe. Regardless of which direction or at what distance we look, on a larger cosmic scale we find similar densities and distributions of galaxies, nebulae, and radiation everywhere. Moderate researchers explain this phenomenon by the theory of cosmic inflation. However, different specialists extend this assumption further with a theory of chaotic inflation. According to this idea, inflation has only stopped in certain regions like bubbles and continues vastly elsewhere. This suggests that different universes might form in these bubbles, each with its own unique physical laws. Within this model, a fundamental question arises. What if the universe does not represent the complete whole, and more imaginatively, what if another universe existed before our own? In that case, the Big Bang would become part of a larger cycle. According to this perspective, our universe is part of a larger multi-layered structure. Within this model, the possibility of an eternal cycle of collapse and rebirth of the universe is advanced. However, this is not the only viewpoint presented in the field of cosmology. Apart from the theory of how things came to be, in 1955 for instance, an article appeared in NASA's Big Times contending that there might have never been a Big Bang, since the universe has existed for an infinite period. In this view, the expansion of the universe would be non-existent, and the continuous development of matter could give the impression of steady growth. Additionally, another intriguing, controversial hypothesis comes from the realm of quantum physics and string theory. Some tests have proposed that our universe and everything in it might be a projection or a higher dimensional simulation. While this might seem like the plot of a whimsical sci-fi film, it could be related to the KF scale, which estimates the level of advancement of a civilization according to its ability to harness energy. If there were a Type 3 civilization capable of fully utilizing the power of an entire galaxy, it might have created a perfect simulation. However, understanding reality in such a scenario is a highly complex matter. Investigating the depths of cosmology and the origins of our universe leads us into a realm of profound mystery and ongoing scientific inquiry. The new pictures captured by the James Webb Space Telescope have reignited discussions about the very fabric of our reality, testing established theories and prompting researchers to rethink fundamental aspects of cosmological understanding. At the core of this inquiry lies the theory of the universe's origin, a cornerstone of modern cosmology. According to this theory, roughly 13.8 billion years ago, the universe emerged from an incredibly dense and hot state, expanding rapidly and giving rise to spacetime and matter as we know it today. This vast event was not just an explosion within pre-existing space but encompassed the very beginning of space itself. The concept of a singularity, where gravitational forces are so intense that spacetime curvature becomes infinite, supports our understanding of this primordial epoch. Yet, the discovery of early galaxies by the James Webb Telescope challenges our assumptions about how rapidly structure formed in the universe's infancy. These galaxies, identified within a few hundred million years of the Big Bang, appear surprisingly mature and massive compared to current cosmological models. One of the key questions raised by these discoveries is the nature of cosmic inflation. According to the prevailing theory, inflation occurred within fractions of a second after the Big Bang, causing the universe to expand dramatically. This rapid expansion would explain the uniformity of the cosmic microwave background radiation observed across the universe today. However, current findings suggest complexities in the early universe's development that may require adjustments to inflationary models. The development of galaxies like those seen by the James Webb Telescope compels cosmologists to reconsider the conditions and processes that govern the universe's early history. These galaxies, now significant in size and mass so soon after the Big Bang, imply a density of matter that exceeds previous estimates. The mystery extends when considering how such massive structures could form and evolve in such a relatively short cosmic time. Furthermore, the discovery of these early worlds raises intriguing questions about the nature of dark matter and dark energy, two elusive components that constitute most of the universe's mass and energy content. While dark matter is believed to provide the gravitational framework essential for galaxy formation, the distribution and properties of dark matter in the early universe remain uncertain. Aligned with these astrophysical mysteries, theoretical physicists are exploring alternative cosmological models that challenge the conventional Big Bang worldview. Some theories suggest that our universe is just one among many in a vast multiverse, each with its own unique physical laws and constants. These ideas, emerging from advancements in string theory and quantum cosmology, propose a more complex and interconnected universe than previously envisioned. One idea gaining traction is eternal inflation, where universes continuously emerge from a larger inflating space. This theory posits that our universe could be just one bubble among countless others, each with its own specific properties. The challenge lies in finding observable evidence to support such speculative ideas, as they push the boundaries of empirical validation. Another provocative theory suggests that our universe exists within a simulated reality, akin to a computer-generated simulation. This concept draws parallels to ideas from information theory and quantum mechanics, where some physicists hypothesize that spacetime and matter could be emergent phenomena arising from an underlying digital code. Such radical hypotheses raise fundamental philosophical questions about the nature of reality and our place within it. While these ideas may seem speculative, they invite exploration into the underlying mechanisms that govern our universe and challenge traditional conceptions of physical laws. Regardless of whether we adhere to the Big Bang Theory, the discoveries made by the James Webb Space Telescope and the continued study of cosmic phenomena compel us to delve deeper into the nature of reality. At the frontier of cosmology, we stand on the threshold of profound revelations about our universe, challenging long-held beliefs and opening new avenues for scientific discovery.